Hello, Paul, and the community of developers dealing with the Arduino now. This is my solution for the challenge. It was about displaying both temperature and humidity on the interface with Python from the Arduino. So I choose here this model. It's a dual needle analog thermometer. That is useful because the needles are crossed. This is what I like, and it shows directly the zone of comfort, or the zone here, which is the zone for the good or the correct expected humidity and expected temperature. You can notice here that we have not the same divisions. It's 1, 2, 3, 4, 5 for the temperature, ranging from -10 to 40. It's Celsius. And for humidity, we go from 20 to 100 here. So 1, 2, 3, 4 divisions only. So let me show you the result first. I will launch my code. So there will be more motivation for following the code then thereafter. Yes, that's it. This is what I came up with. Not very different from original model. And just choose specific colors to show minimal and maximum for humidity and temperature here. And I put the needles in orange, so you can see the zones. You can see humidity ranges from 20 till 100, and temperature here ranges from -10 to 40. So it's more or less the same, and you see here the zone. You can see by yourself that I live in a quite humid place here, so about 68%, and temperature is 17. You can see here the direct output from the Arduino, 17.3 and 68 for the humidity. So yes, it's consistent with measures here. I also played with glass cover here, which is bumpy. You see, it's not a flat glass. So it was a little trigonometrics about this with a sphere intersection, and we'll see all that. So that I hope it makes more sense when we see first the result and then go back in the code. So that's the code now. Here. You notice we have two dials in one. So we have left dial center and right dial center, which are the both origins of the arrows and the hubs, of course. So we start by drawing the hubs here, left hub and right hub. Nothing special here. The text, which is trivial, nothing specific here. We have the needle length, which uses the casing radius. The needle is not at the center of the casing, so the needle needs to be longer than the casing radius. If you see the design here, as we saw just 1 minute ago, you see that this size from this center, the origin of the arrow here, is of course longer than if it was starting from the center of the casing, of the dial, of the main dial. That's why we give multiplicator here. So just to be sure, here you have the casing radius, which is set at 2. Casing radius is the main casing radius, of course. Okay, I hope it makes sense. Thick, length, weight, width, etc. Nothing changes here. Then we have to compute the different values for the left arrow and the right arrow. We see that for the left arrow here, we start from an angular position which is less than 0. -10 here is a little bit lower than the origin of the needle, so it's less than 0 angle. Then we go till where? If we go till here, till 1/2 p, 90 degrees, we would go too far, because 90 degree would be vertical from center here. So we have to compute this angle here. What is the angle between the origin of the needle and, well, the maximum position we have here? Okay, so this is the minimum angle, which I started minus p over 20, and the left max angle here will be 1 on the needle length. Okay, why is it so? If I take here, I will try to use this new tablet. We have, whoa, this is not here. Yes, this is the main dial here. We have left origin and right origin. So left origin will go from here, more or less, till up somewhere here. So what we have to find is the angle that corresponds to the center of the casing here. Okay. What I said just before is that if you go till 1/2 pi, it will go till here, which is too far away. So what we need to know is this one. Okay? And what is this one? We know this. This is the x position of the origin of the needle. And we know this. This is the needle length. So what we need to know, what we need to find, what we need to compute is this. Okay? And we know that in this case cos alpha is equal to what? To the adjacent size over the hypotenuse. Okay, this is what the adjacent side is that we know, and the hypotenuse is here. It's the needle length, and this will give us the angle that we want. hope it makes sense. Okay, so this is what we compute here. Whoop. 1 is just distance. Oops. Or could have taken here directly the center. Yes, you see. We have 1 here. So it will be 1 over the needle length, and we take our cosinus, and that will give us the left maximum angle. Okay. We will need to compute angles and express values from that angle. We express an angle from the values. So we need to know what values represent the minimum and the maximum angle. So we have here the left minimum value and the left maximum value. Okay, be careful, we are talking here about the left dial. The left dial will be displayed on the right scale, but we are talking about the left dial. And the left dial is for what? Is for, where is it? Now the left dial, which is here, is for the temperature. Okay, so the minimum value for the left dial is -10, and the maximum value is 40. That's it. That's what we do here. Then with this, we compute the range. It is the range of values between the minimum and the maximum that this angle will be able to display. It will be the left max value minus the left min value. This is the left range. And we compute here the left span, which is the angular value of the angular value capacity of the left dial. Once again here, if we see the left dial, the angular capacity, well, I call it the span, will go from here till here. And as we said before, it's not half p. Okay, because we start before 0 and we stop before half p. So this span, angular span here, is the left max angle minus left min angle. And with two values, with the physical values here and the span, I can compute here what I call the left angular value. Left angular value will be the left range over the left span. Okay, it will give me the value for 1 degree. What value corresponds to 1 degree? Well, with this factor, I will be able to make a conversion between the value that I want to display and the angle I want to adjust. Okay, I declare here what I call optimum mix min and optimum maximum. This, as you can guess, is simply the values here. Minimum for the temperature, you see it's 17, and the maximum is 23, I think. Yes. So this will enable me to draw those two lines, figuring the representing the optimum zone for the temperature. Okay, the steps is what we used before in your solution already. I can calculate here a step value. Step value will be the range over the left step -1. Okay, then I can go on and draw the ticks as I used to do before with your solution. There's no big modification here. The main modification is that the position here starts from not from 0, 0, 0, but from the left dial center. So we just add the vector, the computed vector here. We just add it to the left dial center, which will give a relative position here. Okay. Yes, then about the same here for the it was for all the little ticks. Little difference here is for the sub-ticks. I use an enumerate like for the previous loop, just because I want to know what tick I am. Why do I want to know that? It's just because I want at a certain tick draw the line for the minimal optimal value and the maximal optimal value. So when drawing all my ticks, if the ticks here corresponds to left optimum min or left optimum max, I can here draw the lines corresponding to those values. Okay, and then we do almost the same for the right one, with just different values for the number of steps here. It's not it's not 6, it's 5 here, because we have 4 divisions. Optimums are not the same, of course, and we also have to invert the process on the horizontal axis, because we draw from right to left. So the way of drawing is just reversed here. And we also have to pay attention to the way we do it, because we will start from the maximum and go to the minimum, as it's an angle going in a counterclockwise natural system. Okay, but it's more or less the same about the algorithm. Okay, that's it for that. Then we draw here the dial. Oh, that is for the glass. The glass is also something a little bit special. Maybe I take back a sketch here. How does it work for the glass? We have here our main dial, okay, which is like this. It's the flat one, okay, with the 2 needles here that cross more or less, etc. This is flat. This is the flat dial, the inner dial. What I want to know, if I look on the profile, I will look at it from the profile here. Okay. What I want is a glass over it, but I don't want a flat glass, I want a bumped glass. Something like this. Okay, how can I do that? I have to cross an arc of circle, which at exactly those contact points here. How can I do that? Of course, this arc must be drawn here from a center, which will be more or less lower than the dial plane. Okay, so I choose the distance here. Means that I know the plane, where the plane is, and if I choose here a distance of 5, I know it. So I know that distance here. The radius of my sphere, I don't know. This is what I'm looking for. Okay, the plane here is almost flat. I took here a thickness, but it's we can neglect it. So we can consider here we have the same distance. Yes, we draw this with a big pen here. Okay, so 5 is much more bigger than the thickness of the dial, of course. So it means that I know this distance, which is 5, and I know that distance. Thus, it is the casing radius. I know it by design. I decided it from the beginning, casing radius. So what I need to know now is this. And I know that sinus alpha is equal to, alpha being here, is equal to what? The opposite over hypotenuse. Okay, and that will allow us to compute here this. Okay, what I call the flatness here is the distance between the plane of the dial and the center of my glass sphere. Okay, the glass pro radius here I can find it with Pythagoras theorem. Okay, then I can find the half angular aperture, which will be the arcsinus of the radius over the glass pro radius. Okay, so first I can find this because casing radius plus flatness square root is equal to hypotenuse here. Okay, so I can find this. And when I have this, I can draw an arc of that aperture. Okay, I have here my alpha, which is I call the alpha aperture, which I find is with this. And then I have all I need to draw my arc here. Okay, glass half angular aperture here. So to draw my arc, I use the glass pro radius here, which I computed with the Pythagoras. From first angle, should be half pi minus glass half angular aperture. Okay, so if we look at it here, this is the first angle going like this, and the second angle will use also a half aperture here. That is how I compute it. Okay, so half p minus glass half angular aperture. What you see here. Half p is this one, and you subtract half aperture and you get your angle. If you add a half aperture from half p, you get an angle. Okay, then we just make the extrusion here. Just a little bit of cheating because I use a circle of very, very small radius, and we'll make like a revolution. Okay, then I have to rotate it to put it in the right way. Okay, then it's just here for the brass casing border. I use a triangle and I extrude it all around. Nothing very special. About the data here, I just extract the data. I send the data as a string with a pipe as a separator, so I just split on the separator and I get all the values that I test structure in the three variables here. I just do this here for debug. Then this is a place where I will use my angular value. Remember, at the beginning I computed an angular value, making the ratio between the value ranges and what I call the angular span. So I compute the angle for the left needle, which will be the left minimum angle, plus here what we have to add as a value, so starting from the minimum value, the temperature here, divided by left angular value, and this will give us the angle. Okay, same for the right one. And once again, I can see it. Okay, that's it here. Okay, we are just at the minimum for the ideal temperature, but for the humidity, yes, maybe I can try to. Yes, yes, it changed. Okay, so you can see the values changing. I'm alive. Yes, that's okay. So, the Arduino. I just received my extra camera, but no had time to set it up. So, putting things together little by little. Okay. Well, hope you like it. Thank you for watching, and good evening, everybody. Bye. See you later.